took the, that's the problem with it. That's what she said. So,
Pardon?
I need to buy one.
I actually kind of forgot what it was.
Determined by
What's that?
Yeah, but last time we talked, it was like, oh, there was something else.
determined by
I think it was, you know, Jacobian of this. Anyway.
that's just
Sorry for ask you to wait for an hour soon. When you want to throw in.
No, I mean,
Start.
okay, everyone, welcome to the morning session of our workshop. Our first speaker this morning is Corvino from Lafayette College. Justin will speak on scalar curvature deformation and the Bartnik mass.
Thanks, so, thanks to the organizers of Miao and Yao for the invitation. It's great to be back here. Yesterday, so I went to college and I lived in Boston for 4 years. And yesterday was the quintessential spring day in Boston. Today, I'm not so sure. But anyway, all right. So, so I want to talk about scalar curvature deformation and the Bartnik mass. So, much like Hungzy left off yesterday with a Riemannian talk, and I'm picking up pretty much right where he left off with the Riemannian talk. But a couple slides of the just to give you the overall outline, and we'll sort of get into it. So we'll start with some preliminaries. We'll start off slowly this morning with some just reminding you some things about the constraint equations and the mass. Sort of formulate the Bartnik conjecture about a certain quasi-local mass. Recall what the static equations are, and then in terms of those equations, go over some deformation and rigidity results for the scalar curvature. In the next talk, we'll hear about deformation results for the full constraint operator, and then talk about the formulation of staticity, so the extensions of a certain domain should be static. And we'll try to formulate that. And so again, the idea is to sort of connect the notion of static, so static metric, with scalar curvature deformation. In particular, the ability to bump the scalar curvature up on domains. Critique argument, like the original argument, that extensions of a domain which minimize the mass amongst all suitable extensions should be static. Criticize the original proof and discuss sort of sharpening that claim and the result. Okay, so we'll start with a few obligatory slides on the constraint equations. The initial data for the Einstein constraint is a Riemannian manifold with a metric and a second fundamental form, or a symmetric tensor, satisfying the constraints. And so we're in this talk, I'm going to focus on the Hamiltonian constraint. And that's a purely Riemannian case. I think about k generally in this talk being 0, and I'll take lambda as 0 as well. So we had some talks yesterday with non-zero lambda. Okay, so the vacuum case would be the observed energy density and momentum density be 0. It's the vacuum case. And then for historical, so the maximal case trace k is 0, and then the scalar curvature is non-negative under the dominant energy condition, which in the Riemannian case is that the energy density is non-negative, which is a reasonable physical assumption. So the purely Riemannian case, k is 0, and is the time symmetric case. And the scalar curvature would be 2 rho. The matter density observed should be non-negative. So we'll generally be dealing with scalar curvature non-negative in the talk, and as most of you know, this is where it comes from. There's a lot of interesting theorems about non-negative scalar curvature. If you want to solve the vacuum constraint on the nose, that's scalar curvature equals 0. Okay. Furthermore, we'll be dealing with asymptotically flat initial data sets. So you have coordinates near infinity where the metric has a fall off. Star means some number of derivatives. And the second fundamental form also has a fall off 1 degree faster. With decay rate bigger than n minus 2 over 2. In general, most of the slides, most of the discussion, you think about the dimension of the manifold being 3, so Q should be bigger than a half. And I'll point out where, try to point out where certain results are dimension dependent, but a lot of it goes through independent of the dimension. So if you go back to with this fall off, as you know, if you go back to the constraints, even if you have k as well, then the scalar curvature falls off faster than it would just from being asymptotically flat. So the scalar curvature would fall off faster, and then if you have rho in L1, non-vacuum case, your scalar curvature would be in L1. And so that's kind of a mass decay condition. So under those assumptions, then we have this formula in 3 dimensions for the ADN mass, really the ADN energy, which is the mass in the Riemannian case. And this is the, say, Euclidean normal and area element of a large sphere. And this expression comes from linearizing the scalar curvature operator at the flat metric. Okay. This is the mass that we'll be using today, the ADN mass. So, remind you the positive mass theorem, Miao, Witten, in 3-manifold asymptotically flat. You can allow boundary, we're dealing with boundary components here. Imagine it's just complete no boundary, or you have to put conditions on the boundary, mean curvature conditions. But just imagine now it's complete no boundary. Then, and the scalar curvature is non-negative, dominant energy condition. Then the ADN mass is non-negative, and the rigidity case is in the flat. So when you have the mass 0, you have Euclidean space. So we'll be dealing with extensions of a region and possibly allowing the boundary of the region to be minimal. And so there's a Penrose inequality, which I'll just state in 3 dimensions. Yeah, asymptotically flat initial data set with the dominant energy condition RG bigger than or equal to 0. If you take an outermost minimal surface, then the ADN mass, so outermost with respect to a given n, is bigger than or equal to the square root of the area over 16 pi. And equality holds in the Schwarzschild case. So if you have a outermost minimal surface and you have equality in the Penrose inequality, then there's one minimal surface, and outside of that, you're the exterior region of a Schwarzschild, positive mass. And of course, I'm not going to get into this, I don't need this here, but this Huskian-Illman sigma is connected, and in Bray there's multiple components allowed. Okay, so that's the preliminaries. If there are any questions, let me know this. All right. So let's go to the Bartnik mass. So the Bartnik mass is a quasi-local mass. So we heard about some quasi-local masses yesterday. I'm just going to talk about this one. The idea is you start with a domain, and so you start with some domain, some boundary, and you want to look at extensions. So here's omega with initial metric g. You want to look at extensions, and g containing this domain isometrically. These extensions are asymptotically flat, non-negative scalar curvature. So, and then you can try to associate, well, you can associate to this then a mass. And so what you have to do to define a Bartnik mass is, first of all, start with a class of admissible extensions. So decide what you mean by a suitable extension of the domain. And then consider all such extensions, look at the ADN mass of those extensions, and then take the infimum over all such extensions. Call that the Bartnik mass. Okay. So the issue is, well, what do you use for the class of extensions? So let's talk about a couple different formulations of that. So one straightforward one would be look at asymptotically flat metrics, think of them as smooth, non-negative scalar curvature. And the original sort of G naught there should have non-negative scalar curvature too. Contain the domain isometrically and say no closed minimal surfaces. And so the idea with the sort of it's called the no horizon condition is that if you allowed minimal surfaces outside the domain, then presumably you could come up with examples of sort of constructions, keep the scalar curvature positive, non-negative, and then enclose your domain, no matter what it was, with a horizon, a minimal surface of small area, and then the mass at infinity is very small, and so your Bartnik mass would reduce to 0. So you have some kind of condition to make sure it's a non-trivial, that the Bartnik mass should be non-trivial, at least at the start. Again, there's another way to define admissible extension. This is from Huisken-Ilmanen in their Penrose inequality paper. So define an extension to be an exterior region. So take an asymptotically flat space with one end, and the boundary is allowed to be a union of closed minimal surfaces, as you have in the Penrose inequality, with no other closed minimal surfaces in the space. Okay, so you've got your domain in there, and the asymptotically flat manifold could have some boundary components that are minimal, right? And then those could contribute to the mass of the extension. So that could be your admissible space. Yeah, so there are various sort of variations on the no horizon condition. No horizon condition is no closed minimal surfaces. You might ask, there's no closed minimal surfaces which enclose the boundary of or enclose omega or homologous to the boundary. So you have some kind of condition like that. They're imposed depending on who wrote the admissible class. Okay, so another approach would be to sort of, in some sense, throw away the domain. I mean, the idea being that the Bartnik mass should basically be determined by the geometry of the boundary. So throw away the domain itself and look at the boundary. So now have extensions be asymptotically flat manifolds with boundary equal to the boundary of your domain omega. Where you have the metric from the exterior agrees with the metric on the boundary. And then you impose a mean curvature inequality on the interior versus the exterior mean curvature. So you want to make sure that the mean curvature measured from outside of this domain, the extended metric, is less than the mean curvature from the inside. So now, as a motivation for this condition, if you want the quasi-local mass to be positive, if you took, I'm not the best at drawing this, as you can already see. Take a negative mass Schwarzschild metric, and then glue it into so take mass negative, and then glue it into a positive mass one. So M positive versus M exterior negative, and then if your region omega was something like this, now you've got a negative mass Schwarzschild end. That could keep the scalar curvature positive. But anyway, this would violate the mean curvature condition. So the mean curvature condition goes the other way. So that's why this rules out something like capping a positive mass Schwarzschild domain with a negative mass Schwarzschild exterior. Anyway, in this case, if you imagine the domain being there, at this boundary you could have a corner, like in this junction here. So you need a positive mass theorem with corners allowed, and the relevant positive mass theorem is due to Xi and Tan and Miao in this situation. setups. The ones that I just outlined, there's 3 different setups. Since you have a positive mass theorem available in either case, then the Bartnik mass is non-negative. And the Bartnik conjecture, at least as far as the minimal mass conjecture, is that, well, there is an extension of your domain in, with whose ADM mass is the minimum of all extensions. Okay? So it sounds simple enough. Bartnik goes on, though, to say the following, that even if you started with looking at smooth extensions, the minimal mass extension may only be Lipschitz across the boundary with non-negative scalar curvature interpreted suitably, in some suitable sense, distributionally somehow. And so this first statement is already kind of an issue in terms of our analysis. The next 2 are sort of more geometric. Outside of the domain, the minimal mass extension should be static vacuum. Okay, so it should be vacuum, R of G should be 0, and static. We'll talk more about static as we go along here. Furthermore, the minimal mass extension, while it may not be smooth across the boundary, should satisfy the geometric boundary conditions. The metrics match up on the boundary, and the mean curvatures, which in the previous case of the admissible class had an inequality, the mean curvatures now are agree from the inside and the outside. Conjecture is such things exist. All right, so this obviously begs a couple questions. One is the minimizer supposed to be in the admissible class, which would be nice. Again, if you just consider smooth extensions, where it would be natural, then Bartnik suggests that the minimizer is going to be outside that class. You might try to define the admissible class in some way to allow corners, like in the sheet 10 Miao positive mass theorem, where the minimizer could actually lie in the class. Another question then is, all right, so if that's the case and if the Bartnik conjecture is true, then you ought to have a class of extensions of domains that are static. So you do not worry about the mass and just worry about producing static vacuum extensions of a domain. And that existence problem, just for static, not for minimizing mass, is already a subtle problem. It's not an easy problem. There's various works that indicate that. But for the rest of the talk, we'll assume we have the existence of some reasonable minimal mass extension and try to say something about it. In fact, we'll try to argue that it's static vacuum outside the given domain. Okay. So although sort of this is known to a number of people, I remember explicitly talking with Hugh Bray years ago that thinking about quasi-local mass, that a minimizing extension for a domain ought to have the property that that extension doesn't admit any localized deformations of scalar curvature upward. So nothing directly about static yet, but just the idea being that that domain should not support sort of the ability to keep the scalar curvature non-negative everywhere, and then be able to add a little bit of matter density positive on some sort of compact set. If you do that, if you have a localized deformation of the metric upward on a compact set, then you produce another extension which near infinity has the same mass. So if the first one was a minimizing mass extension, and this one would be 2. But then sort of well-known, well-used conformal transformation. Oh, yeah, there should be that. It's going to be here. Not both. That's either a minus sign or that 0 is not there. Okay. So anyway, the idea being then take your extension and then modify it by a conformal transformation to bring the scalar curvature down to 0. So you start with some extension, do a deformation. So this is G plus H, and then multiply by a conformal factor. U goes to 1 as you go to infinity, and then U equals 1 on the boundary, and that preserves the metric on the boundary. scalar curvature is 0 if you get this equation, right? And then by the maximum principle, you can argue that the ADM mass comes down. This is a well-known transformation used in the same proof of the positive mass theorem, for example, to squeeze out the matter, bring the mass down. And so that's the idea behind the fact that sort of the minimizing mass extension shouldn't admit localized additions of matter.
Sorry, can you just remind me, what happens to the mean curvature when you do that?
Yeah, I'll get to, so the mean curvature goes down. So part of the issue that I'll be addressing, get to it, is that if the boundary is a minimal surface, then when you do that, the mean curvature just goes negative, and that's bad if you allow this to go to the boundary. So Dan's asking about, so the issue is, right, the conformal method moves the metric right up and including the boundary, and so the issue is what happens to the geometry of the boundary. And in particular, even if they weren't a corner to start, they're going to be a corner now. So, and you have a mean curvature issue at the corner. So the question then is, when you've done this conformal deformation, you produce this extension, is it an allowable extension? You produce an extension, the mass, when you did the conformal change, came down, so it's got lower mass, but is it an allowable extension? Okay. Discussion I had with Pengzi from years ago kind of brought this up. All right. So I'm going to mention, spend a little bit of time talking about how sort of Miao addressed this, Pengzi addressed this, and then I'll bring in the static equations a little bit more before and try to illustrate kind of an approach that I had to this. All right, so Pengzi was looking at say boundaries with metric G. That should be G minus. Should be quasi-convex. So looking at metrics on the boundary, which are positive Gauss curvature and positive mean curvature. So in that setting. So he defines the admissible class to be smooth asymptotically flat metrics, so non-negative scalar curvature, with the boundary, given the boundary of the region you care about, with the metrics agreeing on the boundary, the extended metric and the interior metric, and with the mean curvature condition on the interior and external mean curvature at the boundary. And also then, of course, you're already assuming your mean convex, and with some no horizon condition. So Pengzi proves that if there's a minimal mass extension in this class, which is it's reasonable to assume it's in that class, then the extension is static vacuum. So those are the sort of the exterior equations, and the geometric boundary conditions hold. You've got, well, this is built in, and the equality of the mean curve. So I sort of mentioned a couple of the points to this. First of all, the jump in the mean curvature, so the equality in the mean curvature can be motivated by looking at this equation, the Gauss equation together with the Riccati equation. If you, in the smooth setting, if you look at the mean curvature of a family of hypersurfaces around sigma, you have this equation. So if you have a mean curvature jump at a point on the boundary, that'll make this term distributionally extremely positive. And whatever this is, fine. That makes the scalar curvature positive distributionally at that point or nearby, and then Pengzi finds a way to smooth that out around into the interior and infinity. Okay. Once you've done that, then you can then use the so that handles the geometric boundary condition. Then you've got the scalar curvature positive pushed into the exterior. Now you can use a conformal transformation to bring the mass down. You always have to communicate that to infinity, how the mass is going to come down. Okay. Yeah, let's see. Yeah, right. So there's so anyway, so you solve the conformal. I got a minus sign issue. Okay. All right. So you can do the math. All right. So you solve the conformal problem. You write down the expansion of the conformal factor that solves this, and the mass changes by that factor A in the expansion of the conformal factor. The maximum principle says A is negative, and that governs the change in the mass. One point that I'll mention that Pengzi notes in his paper and also is relevant to the work that I'll present at the end is that if you've got this positive scalar curvature, and it may be large in some places, this conformal transformation to zero scalar curvature might be too abrupt to promise things like the no horizon condition, for example. And so what Pungi does is he sort of connects that conformal change that brings it to zero scalar curvature to, sort of connects it to one that doesn't change anything at all. So in between somewhere for small t, you get a conformal factor which which is a small deformation of 1, pushes the scalar curvature up like you want, and doesn't change the metric that much. And again, the boundary conditions here are preserved under this t deformation. So getting to Dan's question, when you do this conformal deformation, the mean curvature drops. So the mean curvature of the perturbed metric, conformal metric, drops. So more to the point too, then for small t, if the original h was positive, then the h of gt is positive too. You can preserve the positive condition of the mean curvature on the boundary and make it drop, so to preserve the interior-exterior mean curvature comparison. And the mass drop. All right. So that's a really elegant approach, and might wonder why we need anything else. Well, I don't know if we do, but anyway, it always was. Again, to handle the horizon case, the case where the boundary is minimal, you need something else because the conformal deformation drops the mean curvature. So my feeling has always been that you should be able to do the process localized away from the boundary. So you should be able to do some deformation and communicate to infinity the mass, something about the mass here if it's not static, and then do something else to keep the geometry near the boundary fixed. Okay? So kind of roughly speaking, if the exterior were not static vacuum, there should exist asymptotically flat metric extensions, still having the dominant energy condition with smaller ADM mass, but I want to preserve the data, I want to preserve it in a so whatever the extension is, I want to preserve it in a neighborhood of the boundary. So then I can handle, so you can keep any boundary conditions you want, any regularity, whatever you have, you keep. And so if your class of admissible extensions is defined by some interior equations, non-negative scalar curvature, asymptotically flat, and then defined by some boundary conditions, then this kind of deformation will preserve those conditions. One thing I'll also mention, because I won't get to say any more about the details later, even if the minimal mass extension isn't an allowable extension, but the way that we view, and the way that you might sort of view the minimal mass extension kind of coming to exist somehow is take a class of extensions that is an infimizing sequence, and then look at how that sequence, well, this can be subtle. So assuming you know that the sequence converges smoothly on compacts in some reasonable way, except then developing a Lipschitz behavior at the boundary, then as long as the convergence is reasonably smooth, you might be able to run this argument and still show that somewhere along the infimizing sequence, you can produce an admissible extension and the mass drops enough to show that you could not have started with a minimal mass extension. So all those require some estimate. All right. So again, I already mentioned this before, but why localize away from the boundary? So most recently, this came up as trying to handle the case where the boundary is minimal. There's recent work of Mantelidis and Shane producing extensions of sort of minimal boundaries where the Bartnik mass is computed but not achieved. Also, you have, the idea being, right, so if you have a minimal boundary and you have this sort of supposed minimal extension, and if it's going to be static vacuum, then assuming you can formulate it the right way, prove something about the zeros of a static potential, you'd be able to say, well, no, there is no such extension by static black hole, static black hole uniqueness theorem. So there's some subtleties in there, but that's part of the motivation behind the conjecture I stated. All right, so I'll take a few minutes to kind of run through quickly where the static equations come from, and then try to finish with a statement outline of the result. So, okay, so where the static equations come from comes from linearizing the scalar curvature operator. We're not dealing with the full constraints. Okay, and then looking at the formal adjoint. And so elements in the kernel of this operator are static potentials, so non-trivial elements in the kernel. Okay. So the idea is of using this in terms of scalar curvature deformation is, at least on, say, closed manifolds, if you use the elliptic nature, overdetermined elliptic nature of L star, then you can split the function space in the image and kernel of the adjoint, and then Fischer-Marsden in their paper from 75, implicit function theorem tells you if the kernel of L star is trivial, so that means you're not static, you have no static potentials, then you can deform the scalar curvature by a small amount. So S measures the deformation size, and then RG is your original scalar curvature, and you can achieve it with a small perturbation on closed manifold. Okay, so an element in the kernel of L star is called a static potential. Sometimes in physics, you look at static potentials that are positive because given a static potential, you have a space-time work product like this. And obviously that degenerates if F is 0. But in terms of the analysis, PD analysis, you look for something in the kernel, and that thing in the kernel could have a zero set, a very special set, hypersurface, for example, but it could be a zero set. Okay, so I won't go through too much of the background, but your constant curvature spaces are static. And you have static products as well. And of course, for us, the Schwarzschild metric is static, and its potential function is 0 on the minimal boundary. So those metrics are static. Okay, so the deformation theorem that connects, so if you remember, I started with, or I mentioned Bray's discussion with me eons ago now, about extensions not admitting like being able to stick some positive mass into the matter density into the interior. To relate that to the static equations, we have the localized deformation theorem from not a long time ago. But anyway, just take a smooth, there's a bounded domain inside a manifold, which is not static. So the kernel of L star is 0 on the domain. And the theorem says, there are various ways to state this. The simplest way is you take a compactly contained subdomain, smooth function of compact support, and some norm is small. Then you can achieve scalar curvature deformation S in the domain omega naught, containing the support of S, right? With the deformation support of H contained in omega. So you can achieve this. It's not a global conformal method. It's a localized perturbation. And that connects you can let S be a small positive function, and that connects with if it's not static, you can push up the scalar curvature a bit. And of course, you can do this, for any epsilon smaller than, whatever this one. So you can have a family of small perturbations that bring a little bit of matter additionally into your space if it's not static. That's the relation to the Bartnik problem. So, I'm not going to say much about the proof, but the main thing analytically in proving that localized deformation theorem is you can very easily get elliptic estimates with no boundary conditions. And that's the key. And then you have to work it. But for the scalar curvature operator, it's very simple. For the full constraint operator, it's a bit harder, but it also works. Also, elements that are in the kernel, static potentials, satisfy a nice ODE along geodesics. And so this gives you a lot of information too. In particular, again, without going through this slide too much, what you can do, and what's important for the extension problem, is the following. So these extensions are not compact. So if you have a non-compact domain that's not static, then you need an argument to apply the original, so you have a pre-compact subdomain in the exterior that stays away from the boundary and away from infinity. You may go out there, but a pre-compact domain is also not static. Even if the scalar curvature is 0, you make that argument, and you can use the basic analysis to show that. So we use that fact. If the extension is not static, then you can find a large compact subdomain that's also not static. Okay. So I'm going to mention one result about rigidity. So what I just mentioned was about deformation. I'll mention one work about rigidity, and then I'll get to more on the staticity of minimal mass extension. So the question about locally deforming scalar curvature in the static condition, sort of a natural one, interesting one. It's often phrased in terms of bumping the scalar curvature up. Bumping it down isn't much of an issue for a number of reasons. And we have the following work that I'm going to cite about scalar curvature bump-ups that are localized. It's a very nice result of Ji Qing and Wei Yuan, which says if you have a static space and a static potential and a point where your static potential doesn't vanish, so there's an R0 positive, and if you look at metrics on a small R ball, which agree with the static metric on the boundary, you've got a scalar curvature inequality, a mean curvature inequality, and small and C2, so localized bumping up of the scalar curvature. Then there's a diffeomorphism that pulls one metric back to the other. So this is kind of a rigidity result, static metrics, for instance, obstructing localized bumping up of scalar curvature. It's very cool. All right, so let me state, and we have a few minutes, the magic of Beamer. State the theorem, and then I'll make some comments. If there's time, I'll give a proof of a simpler version of it. So suppose you have an asymptotically flat manifold, say asymptotically flat should be. So asymptotically flat metric, closed boundary, non-negative scalar curvature, said it twice for emphasis, with scalar curvature integrable. So you have the mass decay condition or something, so you have the mass well defined. So if you're not static, so L star has trivial kernel on M. Okay. Then there's an epsilon positive and a small open set around the boundary. So a region around the boundary you want to preserve. And a family of metrics, G epsilon, which are asymptotically flat. They agree with the original metric in a neighborhood of the boundary. Scalar curvature is not only non-negative, but it agrees with the original scalar curvature of G. The ADM mass comes down from the original metric, and you got convergence of G epsilon to G, smooth on compaction. The idea to have a family of these for small epsilon is to try to establish a no horizon condition, which you can do for n equals 3, and I believe up to dimension 7. So if you had an extension of a domain that was not static, so L star has trivial kernel, then you can produce, if you had an extension, you could produce an extension with smaller mass. Still obeying the curvature conditions, and whatever boundary conditions you had, you preserve. So I'll say a few words about the proof. And if I run out of time, then I won't give the actual proof of a simpler result, which is elementary, but anyway. Okay, so the outline is, so suppose you have some extension and it's not static. Like I said before, you can find a compact domain outside, which is not static, and now use the localized scalar curvature deformation to deform the scalar curvature up a little bit in that domain. All right. So when you do that, because the deformation is supported away from infinity and away from the boundary, the ADM mass doesn't change. Okay. All right. So we have to again, we have to inform infinity that the mass should come down. So we use a conformal factor to do that. Now, the issue is if the scalar curvature is not 0, when you write it correctly, like I wasn't writing before anyway, when you write down the correct equation, it's nonlinear, so it's a little bit harder to estimate. You basically need estimates to control the conformal factor, the expansion at infinity, and then on compact domains, control how close u epsilon is to 1 when epsilon goes to 0. All right? Assuming you can do that, the mass is perturbed by 2 times, in dimension 3, 2 times this a epsilon. By the maximum principle, it's negative. So the mass comes down, the metric agrees near the boundary. That's the metric that was before you did the conformal factor. But now you've got your metric that's conformally transformed. So now what do? Is everybody with me? So we've taken this original data, perturbed it locally by a little positive bump up of scalar curvature, hit it with a conformal factor to bring the mass down. That conformal factor runs into the boundary. But epsilon's small, and we know with good control we're close to the original metric. U epsilon's close to 1. So now what you do is so in some neighborhood, so we have this neighborhood V that's not static, right? The not static neighborhood. What we'll do is we'll glue the original metric back to our conformal metric. Just by the patch the original metric near the boundary, here's G, put it back, and then out here you have U epsilon to the 4th G epsilon bar, or I think I called it tilde. And in between you patch them. And the point is that when epsilon is small, this metric and the original metric G are close. So this metric and this metric, they're close. Neither of them is static. And so what you can do is use a localized perturbation to perturb the scalar curvature in the patching region, perturb the scalar curvature back to R of G. So the scalar curvature of this thing, you solve the nonlinear PDE, if it's nonlinear, to make the scalar curvature R of G. Here it is R of G and they're close. So inside here, the scalar curvature is roughly R of G. Let epsilon go to 0, you approach the scalar curvature. Now use the local deformation theorem to move the metric, the glued metric, with scalar curvature back to R of G here. And now you've kept the mass down at infinity, and you've kept your original metric the same in this neighborhood. And for small epsilon, you say there's no horizon. Okay. So I think I'm out of time to do the poor man's proof of inversion of this. So I'll leave it at that. Thank you.
Any questions or comments?
Next condition on no closed minimal surface. I guess it's important, but on the other hand, is there any physical meaning besides that to make sure it's not trivial?
I don't know. My understanding is that it's just to keep the mass from hiding the geometry behind that. I think that's all. Is that right, Pumsy?
What was the question? I didn't quite hear.
So why about the no horizon condition? Is there something else behind it other than just keeping the mass from being non-trivial?
You mean physically? You mean?
Yeah. I just thought it was keep it from being 0 at the outset.
Well, if you view the exterior region as living in the domain of outer communication, that is, any black holes are behind it, and if you were in a time-symmetric thing, then minimal surface would be a Motz, an apparent horizon living in the domain of outer communication. And, there are results against the occurrence of such things. Space-time results.
You should not be there. You should not be there. That's true. But on the other hand, there should be more physical meaning. I mean, why don't we have some other condition besides this?
Well, in the limiting case, if the extension is static and if there is a horizon enclosing the boundary, no one knows it must be structured.
You don't really know the conjecture is true at this moment. Unless you know it's true, there should be some other motivation. Actually, what was his reason to claim the conjecture is true?
Anyone know? I'm talking to Robert. That I don't know why it should be. And it's the question. And just for which domains it should be true, and is there a unique extension? It looks like maybe it's not. I don't know. It seems rather tricky. I don't know.
Is it obvious that Euro extensions will have no horizons for silence long enough? I mean, it sounds plausible, but
I don't know if it's obvious. You have to do an argument. If you have in dimension 3, if you had these things, you have to keep them. You get to keep them from disappearing with some control in the curvature and area bounds, and rule them out in the limit.
So the theorems would guarantee they will not disappear.
For example, a result of Brian White, also Mike Anderson.
Well, if there is no other question, let's thank Justin.